So my now hopefully my name is Mark van Rijt. I'm a last year PhD student. Actually, I'm so far in my last year that in 6 weeks I will be defending my thesis. So very close to the end. I did my work in the Laboratory of Physical Chemistry under Bert de Wit and Heiner Friedrich, and in cooperation with the Center of Multiscale Electron Microscopy, with help from Paul Bomans, Rick Joosten, Bernard Oosterlaak, who presented a couple of weeks earlier, and Lisette Wijkhuis, who was a student under me and now started a PhD project of herself. So first, I will give you a bit of the background before we can go to the microscopy part. So I work with zinc oxide because the zinc oxide is a material with high technological interest. It has a huge amount of properties and possible applications. Personally, I think the most interesting one is the use in piezoelectric devices, where due to the way the lattice of zinc oxide is built, if you put force on certain directions, you will get an electronic output from it. Typically, zinc oxide can be formed under mild conditions in water, but that's around 70 to 95 degrees. It can both be nucleated and grown in surfaces and in solutions. And one thing that we are very interested in is if we can grow zinc oxide in templates, that instead of these hexagonal structures, we can grow it into any shape we would like to, depending on the template we choose. So that brings a couple of questions. And then first, of course, there are things you need to know before you can grow anything in a template. So in general, what you need to know is the precursor that's initially formed, and if it's a stable species, then how you can get this precursor in your template, and then how you can ensure that the reaction only takes place in your template and not most of the reaction takes place in the solution surrounding it, so all the reagents are pulled from your template. And an important step into getting here is to understand the mechanism of zinc oxide nucleation in dispersion really well. And the method we use to make zinc oxide here is a relative standard one. We use a zinc salt and we mix that with HMTA. Let's see if I can, this is a bit better, which is this cubic molecule. And if you expose it to elevated temperature in water, it decomposes very gradually into ammonia and formaldehyde. The ammonia can then react with water to form hydroxides, and these hydroxides can react with the zinc salt to get zinc oxide. So now we know the very basics. So if we perform this reaction at 80 degrees, we get some poorly understood intermediates, and then after a couple of hours, we get these zinc oxide crystals, which have been shown by XRD, SEM, Rijt Tm. They're easily identified. But the core of this work is really looking at how do we transfer from the zinc salt to these pillars. And we use a combination of in situ pH measurements with Cryo Tm to make a map of this. So first, a quick introduction in Cryo Tm. So when you do Cryo Tm, you have these 3 millimeter grids, typically with copper support and in a carbon layer on top of it. And in the carbon layer, there are a lot of small holes where you can suspend your final sample in. We glow discharge these grids to make them very hydrophilic, and then we put a droplet with our sample in it on the grid. We blot it so that you get a very thin layer of about 100 nanometer thick, so that it's thin enough to be electron transparent. And then this very thin layer on the grid is shot in a liquid ethane bath so that it freezes so quickly that you do not crystallize the water, but it does solidify so that you have this amorphous electron transparent layer with your sample suspended in it. Then we put it in a special holder, and then we can put it in the microscope. And that already brings us with one of the first problems that we encountered very quickly in this work. So typically we use copper grids, but ammonia and copper, they can interact. And we found that even in the the 3 to 5 seconds that we expose our solution to the copper grid, we can already influence the copper. So we had to change the supports to gold to circumvent that, which is already something, yeah, that's good to know from the beginning if you do something like this. Then when you select a zinc salt, there can of course be many of them. Some of the most common ones that are used to make zinc oxide are zinc acetate, zinc chloride, zinc nitrate, and zinc sulfate. So before doing all this Cryo Tm work, we took one step back and we decided, let's look first at what products you get, because Cryo Tm is quite time consuming and tricky to perform. So if you have a reaction that you already know that doesn't form the wished product or doesn't form your product in dispersion, then you can save a lot of time on this. So performing it under the conditions we just discussed, we found that we get typical hexagonal pillar-like structures when using acetate and nitrate, and we got this more fluffy platelet-like structures when using the chloride or the sulfate. So of course we also did diffraction on this, and then we found that instead of zinc oxide for the chloride and the sulfate, we got some layer basic zinc species instead of zinc oxide. So we already knew that under these conditions we shouldn't be using these salts. And then we have two left, which is the acetate and the nitrate. And as I told you before, using Cryo Tm, you look at your sample in dispersion. And so we simply looked at the end product, and you can see that when you separate the reaction product from the acetate from the flask and from the nitrate, in case of the acetate, you have this clear dispersion, whereas in the case of the nitrate, most of the product is actually formed on the flask wall. So that means that only the acetate system is really ideal for Cryo Tm. So we put all our efforts in elucidating the mechanism for this one. It seems to be a bit laggy at the moment. Can you still hear what I'm saying?
Yeah, I can hear you, and I can see your mouse moving, just the laser pointer doesn't move with it. So I think it's in the PowerPoint.
I'll quickly try. I'll quickly start the PowerPoint back up.
Don't worry, you have the time.
Yes, so that makes the acetate the most ideal candidate to work with.
It doesn't like this transition. Otherwise, start on the slide next to it and then start your presentation from there. See if that works.
Yes, I'll try that. It's interesting. I never had this problem before.
Technology.
So we went all our efforts in looking at the acetate. So the first thing that we did is just run a normal reaction and then do pH measurements so that we have a map of what we can expect in interesting points. So when we look at the pH evolution, you already see when looking at the blue line, which is zinc acetate and HMTA, you have two transition periods where you have a sharp spontaneous drop in pH. So that's at the beginning where you go from 6.8 to 5.8. And it is about after 2 hours where you go from 5.8 to 5.7. So we expect these to be the regions of most interest. So when taking samples, that's also the regions we focus on most. Now, as you also noticed, it's a reaction performed at high temperature, and in a normal Cryo Tm procedure, you don't really take this into account. So we modified the procedure a bit. So this device you see here, our VitroBot, we could preheat it to 60 degrees. And then we can put our reaction right next to it and then make sure that all the components we need are heated in the VitroBot as long as possible, that they're always at the temperature we need it. And then we quickly find out that although normally Cryo Tm you can do quite quickly a couple of samples per minute, but when you do this at elevated temperatures, you want to record everything, the humidity, the temperature in the VitroBot, it becomes a bit more tricky. So you need multiple people to perform this. So one person doing the actual vitrification and one other person operating everything of the setup. So this is what we did, directly sampling into the VitroBot. And then we also found some additional complications. So when you perform this reaction in a fume hood, you can set your watch to it, and it always takes 2 hours plus minus 5 minutes before you get the second transition. However, the moment you start sampling from some point in the reaction, this shifts to earlier time phases. And as I also told you, for Cryo Tm, you need to have ethane in which you shoot your sample with an electronic lever. And this ethane is only good for, let's say, 10 to 15 minutes. So we also found that we actually need even a third person who constantly makes new ethane batches so that we can perform the reaction when the pH curve indicates that we're at a certain set, so that we always can sample at the corresponding moments of transitions that we want. That also makes it extra clear why it's good to have a different in situ method to compare the progress with. So when we perform the reaction and we do Cryo Tm samples, at the very beginning, we see that we have these faceted small crystals of about a couple hundred nanometers in length. And we did electron diffraction on it. And what you see here is a plot of the electron diffraction data that we got. And you see we have 3 distinct peaks besides the 2 large ones that correspond to the water that's of course also present in Cryo Tm in water. And these could match already to zinc oxide, but we're not completely sure about it. So we progressed the reaction and looked at slightly later times. And we saw that those platelet-like faceted particles had significantly grown in time, forming these many micrometer long structures. And again, when performing diffraction on these, we found the similar signals that we saw initially, but we also found a couple of other signals. And then we matched it with the database, and we saw this hexagonal pattern that could match with zinc oxide, but these other signals, it's more cubic, they match with a layer basic zinc acetate, and you also see that it matches the orientation of the crystal, so that suggests that at the beginning of this reaction, we're not already forming zinc oxide, but we're forming these layer basic zinc acetate sheets that are a bit similar to the structures we saw as the end product for the chloride and the nitrate already from the beginning. Now, when we continue the reaction, we see that the size of these sheets grows, but after an hour, we also start to observe hexagonal pillar-like structures that are zinc oxide. So we start with this layer basic zinc acetate phase, then this phase continues to mature, but we already see some of the end product appear. And then when we go to this second dip in pH, we already see from the onset of the dip that we can actually not really find any more layer basic zinc acetate sheets, but we find predominantly zinc oxide pillars. And that's actually very interesting because that means that from this onset, there's actually a really sharp transition from our precursor phase to the dominant end product. So that arises the question, what happens here? Well, we find some other products, and that's like clusters of some high contrast material. We also find some regions where you see these very thin sheets. And if you zoom in, you actually see that they're composed of many small 3 nanometer particles. And we also see regions filled with clusters of very small nanoparticles. So that implies to us, especially when combining it with diffraction, where you see that these species still match to layer basic zinc acetate, that at that moment in the reaction, the layer basic zinc acetate very quickly collapses and allows for the formation of zinc oxide. Performing the reaction further, we find basically only zinc oxide sheets, really indicating that the entire transition takes place in this 10-15 minute window of the reaction. Now, so we have this layer basic zinc acetate, zinc oxide. Why does this transition occur? One thing that we hypothesize is that you also see in other crystals that above a certain size of your crystals, you start to introduce a higher probability of defects. And when you have this defect in your crystal, you have the risk of when it's probed by other forces, like for example the stirrer bar underneath in your reaction, that it might break from that point on. So that suggests that we think that our layer basic zinc acetate crystals grow up to a certain point, and then because they start to introduce defects, they collapse. Because the crystals dissolve, this promotes the growth of all other present crystals in the solution, that's both layer basic zinc acetate and zinc oxide, which means that the other present layer basic zinc acetate sheets also grow above this point, introduce defects, until this whole phase in a very rapid time is consumed and we only have stable zinc oxide crystals left. There's also, of course, another question which we couldn't explain with Cryo Tm, but it's nice to mention. I think it's why does the acetate form product in dispersion and the nitrate does not? And so we looked at the zinc nitrate evolution with SEM sampling, which is possible and something that grows on surfaces. And we found that instead of forming something like layer basic nitrate, we actually formed wolfingite zinc hydroxide at the beginning, which grew on present surfaces and then likely promotes the further formation of an evolution to zinc oxide on those surfaces later in the process. So to conclude, Cryo Tm could be successfully used to probe the formation of zinc oxide from the initial zinc salts. We saw that this layer basic zinc hydroxide species play an important role, especially when they're able to transform into zinc oxide, because this layer basic zinc acetate phase is able to rapidly dissolve, and indirectly with that promoting the formation of larger zinc oxide crystals. And finally, the formation on zinc oxide on surfaces is due to a different formation mechanism. With all of that, I would like to thank my collaborators. And of course, I would like to thank you all for listening to my presentation here today. And if there are any questions, I would be happy to answer.